Welcome. So, whether you're a grad student spinning up your very first system or, a total veteran computational chemist, we all know that molecular dynamics is a wildly powerful tool. But we've got to face a hard truth right out of the gate. The fundamental goal of molecular dynamics is not to just generate cool-looking movies. The goal is to generate trustworthy, mathematically rigorous scientific insight. So today, we're talking about validation. We are going to transform your MD simulations from pretty animations into rock-solid scientific evidence.
Right, so this is the ultimate question you have to ask yourself. You see, there's a massive, glaring danger in computational chemistry, and it's this. The software is almost always going to give you a result. If you feed it a structure and hit run, it's going to spit out a trajectory. But obtaining a trajectory absolutely does not guarantee correctness. It is the classic garbage in, garbage out paradigm. Just because your protein is wiggling around beautifully on your screen doesn't actually mean the underlying physics are right. And believe it or not, published papers, like peer-reviewed papers, have contained fundamental errors simply because the researchers verified that their simulation ran, but they totally failed to validate that their simulation actually represented reality. Because of that, I want you to literally burn this golden rule into your mind. Never trust a plot you haven't visualized. We're going to be looking at a ton of statistical metrics in this explainer, but visual inspection, that is your absolute first, and honestly, your most critical line of defense against unphysical behavior. Averages and standard deviations, they can so easily hide a catastrophic simulation failure. If you don't look at the atomic movements with your own two eyes, you are essentially flying blind.
Okay, let's dive into this. Here's our roadmap. System preparation, minimization and equilibration, production runs and visuals, statistical validation, and finally, your publication checklist. Starting right off with Section 1, preparing your molecular system. This is the absolute foundation of validity. So validation actually starts before you even hit run. It's kind of like a domino effect. A tiny error in your system preparation, maybe a wrong protonation state or a bad force field match, is going to be fatally magnified later on. Let's look at an incredibly common preparation error, how we add salt. Now, a lot of us use the standard add then neutralize method, right? You add enough ions to reach your target concentration, and then you toss in some extra counter ions to neutralize the box. Well, as the source literature points out, a charged solute actually depletes its surrounding environment of co-ions. So if you just add then neutralize, you're severely overestimating the effective salt concentration, and that can completely destabilize your ligand binding poses. Actually, scratch that old method. Instead, you really should use the SLT-cap method or the incredibly simple split method, where you basically equally redistribute the charge excess of the solute between the ionic species. It takes literally zero extra computational cost, but it accurately models true physiological conditions. Game changer. Moving on to Section 2, minimization and equilibration. Or, as I like to think of it, diagnosing and curing sick simulations. Once your system is actually built, those first few moments of a simulation are make or break. You always start by minimizing the potential energy to remove steric clashes. Why? Well, because if you have overlapping atoms, the intermolecular forces are going to be astronomically huge. If you see a rapid, catastrophic spike, like a total explosion in your energy, within the first few time steps, that is a massive red flag. It usually means you have a bad topology, severe atomic overlaps, or you've chosen a time step that is just way too large. You have to catch that immediately. After that, we equilibrate. We've got to stabilize the temperature and pressure, but how you do this absolutely matters. You really need to avoid weak coupling methods, like the Berenson thermostat for your production runs. Berenson actually fails to preserve the equipartition of energy. What it does is systematically transfer energy to the slowest degrees of freedom, which causes the infamous flying ice cube artifact. That's where your molecule freezes internally, but just rockets through the simulation box. No way, we don't want that. Instead, stick to robust methods that sample the correct physical ensembles, like the stochastic velocity rescaling thermostat or Langevin dynamics. Okay, Section 3, production runs and visuals. This is where we are actively monitoring the trajectory. Now, what's really interesting about the production phase is how we actually measure stability. You need to extract key metrics to prove your simulation is physically meaningful. For instance, you want to see a root mean square deviation, your RMSD, reach a nice plateau. That indicates the overall structure has converged and isn't just endlessly drifting. You'll also look at the RMSF to identify which specific residues are highly flexible loops versus rigid structural cores. You'll track the radius of gyration to make sure your protein isn't artificially blowing up or shrinking.
And if you're in the NPT ensemble, checking that your density has stabilized to experimental values, that is a non-negotiable sanity check. We completely expect natural, healthy fluctuations, but continuous volume expansion or wild, runaway temperature drift, those are fatal errors.
And hey, this brings us right back to our golden rule, doesn't it? You must interactively watch your trajectory. A numerical average might tell you the density is perfectly fine, but then you visually inspect it, and bam, you see vacuum bubbles forming in your water box. Or an RMSD plot might look like it's plateauing beautifully, but when you watch the movie, you realize the ligand has completely escaped a binding pocket and is just floating out in the solvent. Watch out for protein unfolding, broken secondary structures, and those sneaky periodic boundary condition artifacts. If you don't watch the movie, you are absolutely going to miss the plot holes.
Which brings us to section 4, statistical validation, because just looking stable isn't enough. We have to mathematically prove our results.
Even if everything looks stunning, we still have to prove it's sampling the correct physical ensemble. And this brilliantly illustrates the hidden danger of the time step trap. Notice how the drift of the effective enthalpy grows significantly as the integration time step increases? The customary procedure for a lot of folks is to just use the largest time step possible so they can get their data faster. But pushing your time step too high introduces totally unacceptable sampling errors, and it just ruins the physical validity of your target ensemble. So yeah, you might be getting your data faster, but that data is fundamentally wrong.
1. Just 1. I want to be perfectly clear about what the number 1 means in molecular dynamics. One single simulation is not evidence. I'll say it again. One simulation is not evidence. A single trajectory could just be trapped in some local energetic minimum. To prove statistical convergence, you absolutely unequivocally must run independent replicate trajectories with different starting velocities. This is how you establish error bars, this is how you calculate confidence intervals, and this is how you prove that your sampling is actually robust.
And finally, section 5, the publication checklist, your very last review before you face the reviewers.
Let's do a rapid-fire cheat sheet for when things inevitably go wrong, essentially a troubleshooting matrix to diagnose crashed runs. So if your protein unfolds immediately, you likely have the wrong protonation state or a force field mismatch. If your ligand just flies away instantly, check for incorrect parameters or starting pose that was totally unstable to begin with. What if you get an energy explosion? Well, look for overlapping atoms or a time step that is way too large. And if you have an unrealistic density, you probably botched the box setup or just straight up failed the NPT equilibration. Seriously, take a screenshot of this. It's going to save you weeks of banging your head against the wall. So the crucial point to take away is this definitive checklist. Before you even think about publishing, you need to verify your charge neutrality and ensure you've properly modeled ionic strength with methods like SLT-cap or SPLIT. Confirm your energy is truly minimized and your RMSD is solidly converged. Prove your temperature and density are stabilized in the correct ensemble. Look me in the eye and promise you visually inspected the trajectory. Make sure you ran multiple replicas to get that statistical uncertainty. And wherever possible, anchor your simulation back to reality by comparing it with actual experimental evidence, like NMR observables or binding affinities. I want to leave you with this thought to chew on the very next time you fire up your terminal. Are you just generating a movie, or are you doing the rigorous work required to generate true scientific evidence? Validation is the bridge between those two things. Apply these tools to your next computational experiment, demand higher standards of yourself and the software you use, and let's push the boundaries of what computational chemistry can actually discover. Thanks so much for joining me on this explainer, and hey, happy simulating!